Welcome to section 10.2, small sample inferences concerning a population mean. When we're working with large samples, the central limit theorem has our back, smoothing things out and allowing us to use normal distributions with confidence. But what happens when our sample is small, say fewer than 30 observations, and we don't know the population standard deviation? This is where we switch gears and turn to a more cautious, adaptable tool, the student's t-distribution. Think of this as trying to judge the quality of an entire game by playing just a short demo. Maybe a new Apex Legends patch is out, but only a dozen players have tried it. You can't ignore the data, but you also can't leap to conclusions. The t-distribution lets us move forward with statistical reasoning while still accounting for our limited knowledge. In this section, we'll learn how to use small samples to make valid inferences about population means, including how to construct confidence intervals and conduct hypothesis tests using the t-distribution. It's all about drawing meaningful insights, even when data is scarce. Whether you're analyzing Fortnite player times, comparing coffee shop wait times, or evaluating student study hours. With small sample inference, data are limited, uncertainty is higher, and our statistical tools need to adapt accordingly. When your sample size is less than 30, you're in small sample territory, and that means we need to slow down, question our assumptions, and be extra precise. With larger samples, we can lean on the central limit theorem. It tells us the sampling distribution of the mean is approximately normal, even if the population isn't. But with small samples, that safety net vanishes unless the population itself is known to be normally distributed. Even more importantly, if we don't know the population standard deviation sigma, we can't use z-scores anymore. Instead, we use the t-distribution, which is built to handle the extra variability and uncertainty that comes from estimating sigma using the sample standard deviation s. Think of it this way. With small samples, the data have less room to average out extremes. A single outlier can swing your mean or standard deviation significantly. So instead of trusting the smooth symmetrical z-curve, we use the t-curve, which is more cautious. It has wider tails to reflect that extra risk. For example, let's say a small team of 12 beta testers try out a new patch for Apex Legends. If their average playtime goes up, you might want to test if it's a real effect. But with so few players, there's a lot of room for noise. One hyper-competitive player grinding ranked matches could skew your results. That's why we don't rush to conclusions with small samples. We need a statistical method that is flexible and humble. That's where the t-distribution comes in. Let's take a closer look at the structure of a t-test for small samples, our go-to method when we're trying to make an inference about a population mean using a small data set. We always start with two competing hypotheses. The null hypothesis, written as H naught, is going to be mu equals mu naught. It's the statement of no effect, no difference. It's the default claim. This is what we assume to be true unless we find strong evidence to contradict it. The alternative hypothesis, written as H subscript A, is the challenger. It represents what we're trying to find the evidence for. The alternative hypothesis can take three forms, depending on the question we're asking. So our alternative hypothesis can be that mu is bigger than mu naught if we suspect the true mean is greater than the hypothesized value. Maybe you think a new Minecraft mod is making players stay in the game longer. Mu less than mu naught if we suspect it's less than. Perhaps a sleep app reduces the average screen time before bed. Or mu does not equal mu naught if we just think it's different, could be higher, could be lower. This is a two-tailed test, often used when there's no directional expectation. To evaluate the evidence, we calculate a test statistic using the formula that you see here. This tells us how many standard errors our sample mean x bar is from the hypothesized mean mu naught. Remember, because our sample size is small and we're estimating the standard deviation from the sample, we use the t-distribution instead of the normal distribution. For example, Let's say the developers of Elden Ring release a new DLC and claim it doesn't change player behavior, but you're skeptical. You think people are logging in more. You take a small sample of 12 players and record their average hours post-update. If the average jumps from 6 to 7.5 hours, this formula lets us check, is that difference real or just sampling noise? Now that we know how to structure a small sample hypothesis test using the tree distribution, the next question is, how do we know when our evidence is strong enough to reject the null hypothesis? This is where rejection regions and p-values come into play. Think of them as thresholds, cutoffs that help us decide whether our test result is extreme enough to count as statistically significant. Let's walk through the three main testing scenarios. So we have a right-tailed test, meaning our rejection region lies to the right of the critical t-value, t sub alpha. And this would be our fail to reject region to the left. This is used when you're testing if the population mean is greater than some value. For example, you suspect a new version of Minecraft with enhanced lighting effects causes players to stay on longer. If your calculated t statistic is larger, so it's over here, than the critical value t alpha, it falls into the shaded rejection zone. On the right, then you reject the null hypothesis. All right, now for a left-tailed test, we're assuming that we're testing a claim that it's decreased. So now we're looking at negative critical t sub alpha, and our rejection region is on the left, the fail to reject region is on the right. So the shaded rejection region is over here. This is for testing if the mean is less than a given value. For example, you want to test if a recent change in the Apex Legend rank system has decreased average playtime. In this case, you reject the null hypothesis if your test statistic is smaller than negative t sub alpha. That is, it lands in the rejection region on the left tail of the curve. Now, a two-tailed test, we want our rejection region to be on both sides. We're rejecting here and here, and our fail to reject region is there. So I'm going to shade here and shade here. But we've only got one alpha, and we've got two t's, a negative and a positive. So we split the alpha. This is alpha over 2 instead of just alpha on each side. This is the most cautious approach. You're testing whether the mean is different from a given value, either higher or lower. For example, a streaming service might claim that the average viewer watches 3 hours per day, and you want to test if the new Dune series has changed that in either direction. Here, you reject the null if the absolute value of your t statistic is greater than the critical value on either side. So you're looking at both tails of the distribution. And here's an alternative approach. Instead of comparing the t-value to a cutoff, you can look at the p-value. If the p-value is less than your significance level alpha, commonly 0.05, that means your result is rare enough under the null to reject it. Imagine you're in court. The null is the defendant being presumed innocent. To convict or reject the null, the evidence, your t-score, has to be far enough from normal to fall into the guilty zone, the rejection region. The p-value is like a score of how rare that evidence would be under innocence. If it's rare enough, you've got a case. All right, for example, let's say the Fortnite development team wants to know if a new matchmaking algorithm is making matches last longer. The null hypothesis is that there's no difference. If their sample of 25 players shows a big enough increase in match duration, their test statistic might land in the rejection zone. That's their signal to reject the null hypothesis and move forward with the update. Let's talk about a key concept in using the t-distribution, degrees of freedom, or DF. Degrees of freedom determine the shape of the t-distribution curve, specifically how spread out or peaked it is. Mathematically, when we're working with a single sample mean, the formula is degrees of freedom equals n minus 1, the sample size minus 1. That simply means we subtract 1 from our sample size to get our degrees of freedom. Why subtract 1? Here's the idea. Imagine you're collecting data on daily playtime from 5 Apex Legends players. If you know the total playtime and you've already been told the first 4 values, then the 5th one isn't really free to vary. It has to be whatever value makes the average come out right. That's why we lose 1 degree of freedom. So why does this matter? Because small degrees of freedom make the t-distribution more cautious. With fewer data points, we're less certain about how accurately we're estimating the population mean. The result? Thicker tails on the t-curve, meaning more room for extreme values. This helps protect us from drawing overly confident conclusions based on small samples. If DF is small, like 4 or 5, the t-distribution is wide and flat, allowing for more uncertainty. As DF increases, the curve becomes more like the standard normal z-distribution. Once we get to around a DF of 30 or more, the t-distribution and the z-distribution are almost indistinguishable. All right, think of a squad of 5 Apex Legends players trying a new strategy. If 4 of them share their result, how many kills, how much time they spent, the 5th player's stats can't be random anymore. They're locked in to make the team average work. That's what degrees of freedom represents. How many data points are actually free to vary once the average is set? All right, let's take another moment to talk about the critical t-value, which is one of the most important pieces of information you'll pull from a t-table during a hypothesis test or confidence interval construction. The critical t-value is the number that tells you where the boundary lies. That is, the point beyond which your result is considered rare enough to reject the null hypothesis. Think of the critical t like a boss fight in a game, like Elden Rings or Dark Souls. You don't fight the boss just for fun. It's a signal that you've hit a turning point. If your calculated t-score crosses this value, you're entering the rejection region, meaning your data is extreme enough to challenge the null. Before we dive into applying the t-distribution for real problems, let's make sure we're playing by the rules. The t-distribution is powerful, but only if the conditions are right. Here are the 3 key assumptions you must check before using a t-distribution. First, the data must come from a random sample. This ensures that your results are unbiased and can reasonably represent the larger population. If your data only comes from your roommates or a Reddit thread you follow, that's not random, and your results might be misleading. Think of it like a fair loot box in a game like Fortnite. If you're not pulling items at random, your results are rigged from the start. Second, the population the sample comes from must be approximately normal. This doesn't mean the sample itself has to look perfect. Small samples are often messy, but we must believe the underlying population is normally distributed. If you're testing something like how long it takes players to finish a new level in Elden Ring, and you know from developer data that completion times usually follow a bell-shaped curve, you're good. But if your data is wildly skewed, maybe due to a few speedrunners or trolls, using the t-distribution might not be valid. Third, you should only use the t-distribution when the sample size is small, typically fewer than 30 observations. Why? Because the whole point of the t-distribution is to compensate for the extra uncertainty we face when we don't have a lot of data, and we don't know the population standard deviation. So if you're analyzing feedback from just 12 Minecraft mod testers, or trying to evaluate how long it takes 9 players to complete a new Dark Souls boss fight, this is the perfect situation to use the t-distribution. In summary, if your sample is random, your population is normal, and your sample size is small, then t is your go-to tool for drawing inferences about the population mean. Let's work through a full hypothesis test using the t-distribution, and we'll anchor it in a pop culture scenario that might feel a little too real if you're a sci-fi fan. Suppose you're part of a Discord group that hosts weekly Dune lore marathons. Think film clips, deep dives into the Bene Gesserit, and way too much discussion about sandworms. The group claims these sessions last 2.5 hours on average. You're skeptical. You feel like these meetings stretch on well past the 2.5 hour mark. So you collect data on 8 recent sessions and find the sample mean is 2.9 hours and the sample standard deviation is 0.3 hours. Now the claimed population mean is 2.5 hours. That's our mu naught. Let's test whether the sessions actually run longer than claimed. So first, we're going to state the hypotheses. So our null hypothesis is mu equals 2.5 hours. This says the marathons are exactly as long as advertised. Our alternative hypothesis is mu is bigger than 2.5 hours. You believe they're longer. So this is a right-tailed test. Now, knowing it's right-tailed, that means on a normal curve, our rejection is over here on the right. Now we're going to compute the test statistic. So we'll use the formula for the t statistic. R value is 2.9 minus the claimed value is 2.5 over R sample standard deviation 0.3 divided by the square root of R sample size 8. We get a t-score of 3.77, which is quite high. It tells us the sample mean of 2.9 hours is more than 3.7 standard errors above the claimed value. All right, we want to determine the rejection region. So our degrees of freedom are going to be n-1, so 8 minus 1 is 7. From the t-distribution table, the critical value for a right-tailed test at alpha equals 0.05 with 7 degrees of freedom is approximately 1.895. So this cutoff here would be the 1.895. But now what we found is way over here at 3.77. Since 3.77 is bigger than 1.895, we're way into that rejection region. So our conclusion, we reject the null hypothesis. That means there's strong statistical evidence that the Dune-Lorne nights do run longer than the group claims. Maybe it's time they admit the truth, or at least add in some snack breaks. Okay, let's dive into another full hypothesis test example, this time set in the pixelated world of Minecraft. Suppose a new mod claims to make Minecraft more efficient. Maybe it optimizes resource gathering, speeds up building with auto placement, or compresses day-night cycles. In theory, this should reduce playtime, and that's exactly what we want to test. So you sample 10 players using the mod and find the following. Sample mean X bar is 2.4 hours per day. Sample standard deviation S is 0.6. And of course, our claimed population mean mu naught is 2.8 hours per day. Go ahead and pause the video here and try for yourself. Resume the video when you're ready for the solution. All right, our first step is to set up the hypotheses. So mu equals 2.8, the claim. Our alternative is that it's less than, which means this is a left-tailed test. We want to see if the average playtime is less than what it used to be. Okay, so mu equals 2.8. That's no change in the playtime. Mu is less than 2.8. That's the mod decreases the time. Now we're going to compute the test statistic. We calculate the t-score. Our value was 2.4 for our mean minus the claimed 2.8 over our sample standard deviation 0.6 divided by the square root of our sample size 10. That negative 2.11 score tells us the sample average is more than 2 standard deviations below the claimed mean. That's a sizable difference for a small sample. All right, we're going to compare to the critical value. With 9 degrees of freedom and a significance level of 0.05, the critical value is negative 1.833. So we get negative 1.833 is this cutoff value. A value we found is over here. That's the negative 2.11. We're in that rejection region. All right, so now we're going to compare. Since negative 2.11 is less than negative 1.833, we fall into the rejection zone. So we reject the null hypothesis. That means we have statistical evidence that the mod really does reduce playtime. It's not just hype. Maybe this is the mod to recommend when finals week hits and players need to game responsibly. All right, let's walk through a two-tailed hypothesis test, the kind we use when we want to know if something is simply different, not necessarily greater or less. If you're feeling confident, pause here and try it on your own first, and then resume the video when you're ready. All right, imagine you're working with a paint manufacturer who advertises that 1 gallon of their paint covers 400 square feet. You're suspicious. Maybe you've seen some patchy walls or inconsistent reviews online. So you randomly test 10 gallons, and here's what you find. Your sample mean is 377.2 square feet. Sample standard deviation is 42.6. Of course, your mu naught, the claim, is 400 square feet. We're not assuming whether the coverage is too high or too low. We just want to know if it's different. All right, so we set up our hypotheses. Since this is a two-tailed test, we phrase the hypotheses accordingly. Mu equals 400 is our null, and mu does not equal 400 is our alternative. We're asking, is the true average different from 400? Not better, not worse, just different. Being a two-tailed test means on our normal curve, our rejection region is cut in half over here and over here. All right, now we're going to compute the test statistic. So we get T is what we found, 377.2, minus the claim, 400, over our standard deviation, 42.6. That should be a divided by, didn't make it in there, divided by square root of 10. Okay. This t-score tells us that our sample mean is 1.68 standard errors below the hypothesized mean. Now we want to compare that to the critical value. For a two-tailed test with 9 degrees of freedom, because our n is 10, right? So n minus 1, 9 degrees of freedom, alpha equals 0.05. We split that alpha into two tails. So we use alpha equals t of 0.025, half of the 0.05. We get 2.262. So this is a positive 2.262. And this right here on the number line would be negative 2.6262. Now our negative 1.68 would be over here. That's in the fail to reject region. Negative 1.68 is not more extreme, so we do not reject the null hypothesis. This sample doesn't prove strong enough evidence to say the paint's true average coverage is not 400 square feet. Yes, our sample average is lower, but the variability in small sample means we can't draw a firm conclusion. If this were your product, you'd want to test more gallons to be sure, maybe even 30 or more to increase your statistical power. Let's shift our focus from hypothesis testing to estimation, specifically estimating the population mean mu when we only have a small sample and we don't know the population standard deviation. This is where the t-distribution confidence interval comes into play. We use the formula x bar plus or minus t alpha over 2 times this s divided by square root of n. X bar is the sample mean, our best estimate of mu. T alpha over 2 is the critical value from the t-distribution that matches your confidence level, like 95%. S over the square root of n is the standard error, how much the sample mean is expected to vary from sample to sample. Together, this formula gives us a range of plausible values for mu based on our sample. Now, why t and not z? Because we're using the sample standard deviation s, not the population sigma, and our sample is small. We can't rely on the normal distribution. We need the t-distribution, which adjusts for that extra uncertainty. This means our confidence intervals are wider than they would be with large samples. They're more cautious. We're building in more wiggle room because we don't know enough yet to be more precise. For example, let's say you test a new stealth mechanic in Dark Souls and you only have data from 8 players. You find an average success time of 3.2 minutes with some variation. If you want to estimate how long stealth generally takes for all players, you'd build a confidence interval using the t-distribution, not z, because your sample is small and there's still a lot of unknown. You're not shouting, this is the exact time. Instead, you're saying, we're fairly confident the real average is somewhere in this interval. Let's walk through a full confidence interval using imaginary Apex Legends data. Suppose you're analyzing scores from 12 players after a buff patch that developers say should boost overall performance. Your goal is to estimate the true average score for the entire population of players using this update. Since your sample is small, n equals 12, and the population standard deviation is unknown, we'll use the t-distribution. So step 1, you're going to plug in values. You're given X bar is 1890, S is 120, N is 12, and our degrees of freedom, N minus 1, would be 11. For 95% confidence and 11 degrees of freedom, T alpha over 2 would be the T that corresponds to 0.025, half of the 0.5. 0.5 because it's a 95% confidence interval, right? So 5% remaining becomes 0.05 when we change from a percent. And then dividing that in half gives me the 0.025. All right, so we look it up from a table or use technology, we get 2.201. Now calculate the standard error. So we're going to do S over the square root of N. That's our S is 120 over the square root of our N is 12. We get 34.64. Build the confidence interval, right? We got to get the margin of error to build the confidence interval. So our margin of error, it was just multiplying that 34.64 we found by the T we looked up, right? And we get 76.25. Now our confidence interval is our mean from our sample, 1890, plus or minus this figure we just came. That gives us this intervals of values, right? So we are 95% confident that the true mean score after the buff is between 1,813.75 and 1,966.25. Now, let's make a connection here. We could also use a confidence interval to perform a hypothesis test. Suppose you knew the pre-buff average was 1,800 and you're wondering if the buff improved that score. Since this entire interval is above the pre-buff average of 1,800, we would have strong evidence that the buff has had a real positive effect on player performance. You're essentially beta testing this patch like a QA team. This confidence interval lets you estimate how real players are performing in the wild and helps you decide if the buff should stay or be nerfed. The t-distribution gives you a mathematically sound way to make that call when your data set is small and uncertain. Let's wrap up what we've learned about small sample inference, a powerful set of tools that helps us make reliable decisions even when our data is limited. When you're working with small samples, usually fewer than 30 observations, and you don't know the population standard deviation sigma, which is most of the time in the real world, you should turn to the t-distribution instead of the normal z-distribution. Why? Because the t-distribution is built to adjust for the extra uncertainty that comes with smaller data sets. It has fatter tails, which gives you a buffer for the greater variability you can expect with limited information. It's a bit like taking a more cautious approach. The t-distribution protects you from jumping to conclusions too fast. Before you use it, though, check the assumptions. Did you collect your data from a random sample? Can you reasonably assume the population is normally distributed? If those boxes are checked, you're good to go. You can use the t-distribution to do both types of inference. Build confidence intervals to estimate a range for the population mean, and conduct hypothesis tests to evaluate claims about that mean. Whether you're testing if a new Elden Ring patch increases average boss clear time, or if a limited edition Dune merch drop caused students to stay up past midnight more than usual, small sample inference gives you the statistical firepower to draw valid conclusions from modest data.